In this video, we will be introducing the notion of the continuity of a function. Let's start with the intuitive idea of continuity. Intuitively, a function f is continuous if its graph can be drawn without picking up your pencil. This will mean that the graph has no jumps, no holes, no breaks, no vertical asymptotes. Consider the function with the given graph. Take a second to find all of the places where you think this function has a discontinuity. This function has a discontinuity when x equals -4 because there is a jump in the graph. A second discontinuity occurs when x equals -1 because there is a hole here. A third discontinuity when x equals 0 because there is a vertical asymptote. And one final discontinuity when x equals 4. If you were to draw this graph, then each of these are the x values where you would have to pick up your pencil to continue drawing. Now that we have an intuitive understanding of continuity, let's state the formal definition. A function f is continuous at a number c if the limit of f of x as x approaches c is equal to f of c. Let's say that one more time. A function f is continuous at a number c if the limit of the function as x approaches c is equal to the value of the function at c. There are actually three claims being made in this statement. Let's look at them individually. According to our definition, a function f is continuous at a number x equals c if, first, the limit of the function exists as x approaches c. Secondly, the function is defined at c, that is, f of c exists. And finally, the value of the limit at c is equal to the value of the function at c. So from here on out, whenever we want to talk about the continuity of a function, instead of using our informal language such as holes and jumps, we will refer to the three conditions of the formal definition. The limit must exist, the function must exist, and the value of the limit must equal the value of the function. Note that if one or more of the three conditions fails, then we say that f is discontinuous at x equals c, or that f has a discontinuity at x equals c. Let's return to our example function from earlier. Previously, we found each of the discontinuities of this function intuitively, but now we can give a formal reason for why each is a discontinuity. Remember that we only have three possible reasons why each is a discontinuity. We must say that either the limit does not exist, the function does not exist, or the value of the limit does not equal the value of the function. Our first discontinuity was when x equals -4. Notice that the limit as x approaches -4 from the left does not equal the limit from the right. Therefore, based on our formal definition, we see that f has a discontinuity when x equals -4 because the limit of the function does not exist as x approaches -4. Our second discontinuity is when x equals -1. Notice that the limit does exist here, but the function is undefined. Therefore, we will say that f has a discontinuity when x equals -1 because f of -1 does not exist. Our third discontinuity occurs when x equals 0. From the graph, we see that the function has a vertical asymptote when x equals 0. Therefore, we will say that f has a discontinuity when x equals 0 because f of 0 does not exist. Our final discontinuity occurs when x equals 4. We see that the limit as x approaches 4 does exist, since the limit from the left equals the limit from the right here. We also see that f of 4 is defined. However, the value of the limit does not equal the value of the function. Therefore, we will say that f has a discontinuity when x equals 4 because the limit of the function as x approaches 4 does not equal the value of the function f of 4. Now that we've explored continuity from the graph of a function, let's look at a few examples given the equation of a function. For our first example, we want to determine whether the function x squared minus 16 divided by x minus 4 is continuous at x equals 4. Using our definition of continuity, we will first check whether the limit of the function exists as x approaches 4. Recall that our first step in computing a limit is always to evaluate. When we plug in x equals 4, we get 16 minus 16 divided by 4 minus 4, or 0 divided by 0. We must go on to determine whether the limit exists. We must simplify. Since we have a rational function, let's factor. We can factor the numerator into x minus 4 times x plus 4. Canceling the x minus 4 term from numerator and denominator, we are left with the limit as x approaches 4 of x plus 4, which, after evaluating, is 8. So the limit does exist as x approaches 4. Our next condition in the definition of continuity is to check whether the function exists when x equals 4. When we evaluate at 4, we get 16 minus 16 divided by 4 minus 4, or 0 divided by 0. This is not a well-defined number, and so f of 4 does not exist. Hence, our answer is that the function f is not continuous at x equals 4 because f of 4 does not exist. For our second example, we want to determine whether the given piecewise function is continuous at x equals 2. F is defined to be the line x plus 3 for values of x which are less than or equal to 2, and 2x plus 2 for values of x which are greater than 2. Appealing to our definition of continuity, we must first check whether the limit exists when x approaches 2. Since f is a piecewise function with different definitions to the right and left of 2, we will use one-sided limits. First, let's find the limit of f as x approaches 2 from the left. Since we are approaching x equals 2 from the left, we want to use the definition x plus 3. Evaluating, we see that the limit from the left equals 5. Now let's compute the limit of the function as x approaches 2 from the right. Here, we will use the definition 2x plus 2. Evaluating, we see that the limit from the right is 6. Since the limit from the left does not equal the limit from the right, we know that the limit of the function does not exist as x approaches 2. Therefore, our answer is that f is not continuous at x equals 2 because the limit of the function does not exist as x approaches 2. For our final example, let's change our piecewise function slightly so that f is defined to be x plus 3 when x is strictly less than 2, 4 when x equals 2, and 2x plus 1 when x is greater than 2. Following our definition of continuity, we first check whether the limit of f exists as x approaches 2. When we approach 2 from the left, we get the limit of 5. This time, when we approach 2 from the right, we also get 5. Therefore, the limit of the function does exist as x approaches 2 and equals 5. Our second condition for continuity says that we must check whether the function exists at x equals 2. Based on our definition of f, we see that when x equals 2, the function is defined to be 4, and so f of 2 equals 4. Okay, so we found that the limit of the function as x approaches 2 equals 5, and the value of the function at 2 is 4. Our third and final condition required for a function to be continuous is whether the value of the limit equals the value of the function. Does the limit of f as x approaches 2 equal f of 2? Well, we found that the limit of f as x approaches 2 equals 5, and the f of 2 equals 4. Therefore, no. The value of the limit does not equal the value of the function when x equals 2. And so our answer is that f is not continuous at x equals 2 because the limit as x approaches 2 does not equal f of 2. That concludes our introduction to the continuity of a function. We will look at more complicated examples during class. I'll see you there.